Hi everybody around the world, and thank you for joining our 5th webinar of our webinar series Hoppy Topics. My name is Sandro and I'm working for the technical support at Hopsteiner, Germany. For everybody who's joining for the first time, I'd like to give a very short introduction. Our webinar series is a free online seminar with presentations about various hop-related topics. Due to the fact that it's still difficult to meet each other in a way all of us would like to, we have decided to additionally offer this kind of online support. In this way, we want to keep you up to date about the latest research in hops. Before I introduce the speaker of today's presentation, everybody should know that questions and comments are absolutely welcome. Your microphone and your camera remain switched off, but you can address your questions anytime during this webinar in a written form through the Q&A tab on the right side of your screen. I will pick them up in the end of the presentations where we have time for discussion. The presentation will take about 45 minutes, followed by discussion, so in total we have about 1 hour. And after closing the webinar, you have the chance to give us a very short feedback by answering 2 questions if you like to do so. Here with us today we have Dr. Martin Biendl, our head of the R&D and Analytical Department in Hopsteiner, Germany. Martin received his PhD degree in organic chemistry from Regensburg University in 1990. His research experience covers hop-related needs for the brewing industry and beyond, such as the outstanding xanthohumol research. He is the representative of the International Hop Industry Corporation in the EBC Analysis Committee and since 2001, chairman of the Hops subcommittee. As EBC representative, he is also co-chairman of the International Hop Standards Committee. In 2007, he was elected to the board of the Association of the German Hop Trade. Besides of many papers published in the international brewing journals, he is also the co-author of 2 books representing the full range of hops. Martin, as you know, my role is also to manage the incoming questions, and I have already 2 to start with. So, how is the growing conditions of the hops actually, and what is the topic you talk today?
Okay, hello everybody, good morning. I'm actually here in my office in Mainburg, surrounded by hop gardens, so I can give you the feedback and the information that the hops are growing very well at the moment. We had, especially in June, a lot of and enough rain, so everything looks good, and we hope to get a good harvest this year, and so that we have enough hops even for dry hopping. And dry hopping, this is the topic of my talk today. I will inform you about the analysis of dry hop beers and try to solve this problem and what is special here in with regard to dry hop beers. So, how to analyze dry hop beers? To be able to answer this question, we have to give some definitions in the beginning. The first question is which hop compounds are relevant to the flavor of beer? So which one we have to analyze actually? And we all know that there are the 2 categories, non-volatile compounds. They are more responsible for taste, especially bitterness. And the volatile compounds, they are more responsible for the odor or the aroma of the beer. As soon as we know which parameters to analyze, we have the question, is it possible to add on these parameters to existing suitable analytical methods, or is it necessary to develop new methods? I think what we all know is that the non-volatile compounds are analyzed by high performance liquid chromatography usually, and the volatile compounds are usually analyzed by gas chromatography. So this is the basic information we all have. Let's start with the relevant compounds. So which are the relevant compounds to be analyzed? And there is in aroma science a definition, so-called key flavor compound is a compound, in this case, with the concentration in beer higher than its bitter or its aroma threshold. And when we look at the 2 beer types, beer without dry hopping, you see a very limited number of key flavor compounds with regard to the bitterness, we have the resins, but only the iso-alpha acids or their reduced form, respectively. And with regard to the volatiles, we have linalool. And it's much more in the case of dry hopping. If you do dry hopping, in addition to late or wort hopping, you get several more compounds introduced to the beer. With regard to the resins, you get the alpha acids, the humulinones, the holopones, and the xanthomol. With regard to the flavonoid fraction, you get glycosides of quercetin, camphorol, and multifidol. And with regard to the volatiles, you get myrcene, geraniol, several esters, and several thiols. And this slide shows you why, it's not easy to analyze dry hop beers, why this is a complex matrix to be analyzed. Some more information on the hop-derived key bitter compounds in beer. The thresholds of these compounds are usually in the ppm range. This means in the milligram per liter range. In every beer, you have the iso-alpha acids or the reduced forms, the iso-alpha acids respectively, rho, tetra, or hexa. This is what we know from every beer. But as I told you and I showed you before, with regard to dry hop beers, we have in addition the alpha acids. Fritsch and Schellhammer have reported on the bitter thresholds of these compounds in 2007. We have the holopones, a German group has researched on this and published in 2009. And we have the humulinones. Again, the Schellhammer group identified them as key bitter compounds. These three compounds are from the so-called soft resin fraction of hops. And the alpha acids are then during wort boiling converted to the iso-alpha acids. So they also count to the, let's say, to the soft resin fraction. All these compounds here have bitter thresholds in beer in the range of 5 to 15 milligram per liter. And in addition to these compounds coming from the soft resin fraction of hops, a rather recent paper reported on some compounds in the hard resin fraction of hops. So these are the more polar compounds that also contribute to beer bitterness. There is the fraction of some flavonoids, glycosides of quercetin, camphorol, or multifidol. And there is the fraction of the brenylated flavonoids like xanthomol and isoxanthomol. So these are the basic research to define these key bitter compounds in beer. Now to the aroma compounds. Here it's important to know that these compounds are present in beer and can be key aroma compounds in a factor of 1,000 to 1 million lower as compared to the bitter compounds. We have some compounds in the ppb microgram per liter range, and we have some compounds even in the ppt nanogram per liter range. As I told you before, linalool is a key aroma compound also in regular beer, non-dry hop beers. Fritsch has done some research and discovered this in 2005. He also made an experiment with dry hopping and identified myrcene as a key aroma compound then in dry hop beers. Geraniol was identified by Kishimoto. It comes not from all hop varieties, but from some of the hop varieties. Then we have various esters, for example, 2-methylbutyl isotanoate. We have some thiols. The most important and well-known one is the 4-mercaptomethylpentanone. And we have several more thiols also researched on by Kishimoto Takoi from Japan. So now we know which parameters we have to analyze in dry hop beers. The next question is there a suitable existing method, or is it necessary to develop new tools and new methods? And for hop resins, we know there are existing EBC methods with HPLC-UV. The question is, can this use for dry hop beers? For hop flavonoids, the question is open whether these can be analyzed by HPLC-UV, or is it necessary to use more sophisticated HPLC-MS equipment. For hop aroma compounds, the question is, can we use GC-FID, flame ionization detection, or is it necessary to use GC-MS methods? Is it possible to analyze the beer samples by headspace sample preparation, or is there a more sophisticated sample preparation necessary? And the question is also if GC-MS is okay, or if we need a combination with GC-MS-MS. So these are the open questions. Let's start with the hop resins, and the question, can they analyzed by HPLC-UV? And there is already an existing HPLC-UV method in Analytica EBC. It's the method 9.47, determination of iso-alpha acids and reduced iso-alpha acids in beer. Short description of the method: there is a dilution of the beer sample with methanol, and then you have some precipitation, and this has to be separated by centrifugation, for example, and then you can inject this sample directly to the HPLC. In this case, a C8 column is used, and a detection wavelength of 270 nanometer, and the eluents are methanol and acetonitrile citric acid mixtures. Here you see a chromatogram of a non-dry hopped beer, in this case a Pilsner beer, and you see the separation according to this method 947. You have several peaks. This is the cis co-isohomolone, the trans co-isohomolone, the cis-at isohomolone, the cis-N isohomolone, and trans-at and N isohomolones. And there are no more hop compounds currently known as key bitter compounds of beer present in this chromatogram, and this is not necessary because we have no more. I make the comment there is no single hop compound, because there is always the possibility that several minor components have additive effects and then are also contributing to a taste or aroma. But with regard to single compounds, the current knowledge is that we have no more. The exception are the beers with the reduced iso-alpha acids, but then you see the reduced iso-alpha acids in addition or instead of the iso-alpha acids. Okay, so it seems to be very simple with regard to the regular beer. And now we look again to the composition before and after dry hopping. And this is in this case a pale ale, kettle hopped with Hallertau tradition, pellet type 90. And you see the typical composition. You see no humulinones, lupulones, xanthohumol in this beer, or they are below the limit of detection of the method. You have traces of alpha acids, and you have iso-alpha acids and isoxanthohumol. Iso-alpha acids are built from alpha acids during wort boiling, and isoxanthohumol is built by xanthohumol during wort boiling. And after dry hopping, here we did additional dry hopping with 500 gram per hectoliter of the US variety Bravo, also pellet type 90. And you see some differences in the composition. With regard to iso-alpha acids and with regard to isoxanthohumol, you see almost the same concentration. There is no more compounds are introduced by dry hopping. With regard to iso-alpha acids, usually the concentrations even go down because the hop matrix, the hop powder, absorbs some of the iso-alpha acids. And but the picture is then completely changing. And also for holopones and for xanthohumol, we have higher concentrations. But as I told you before, for holopones, the bitter threshold is in the range of 5 to 15, and therefore there is no contribution, direct contribution to bitterness. Therefore, this is not judged as very important. And for xanthomol, the bitter threshold is also higher than 0.7. And the key bitter compounds in dry hop years are mainly the alpha acids and the humulinones. They are introduced to concentrations, in this case, up to 15.7 milligram per liter or 10.8 milligram per liter respectively. And with the knowledge from literature, they are key bitter compounds in this beer type. So we have to carry about the analysis of these compounds. So the question is whether you can do the dry hop analysis also with the existing 947 method. And to make a longer story short, this is possible. And in the meantime, the EBC has already organized an international collaborative trial with participation of the analytical committees of the Americans, the ASBC and the Japanese, the BCOG, and the collaborative trial has been successful. And very soon there will be a more or less identical method to the 947 recommended for the analysis of bitter compounds in dry hop beers. The number will be 9.50, and this will be an international method, also recommended by ASBC and BCOG in the end. And what is different to the existing EBC 947 method is especially then the type of calibration standards you need, because before introducing the method, it was necessary to develop and release new international calibration standards. I think you know these international calibration standards for iso-alpha acids, reduced iso-alpha acids, and this range is now enlarged by the ICS HUM1 for humulinones, the ICS X1 for xanthohumol, and the ICS A1 for alpha acids analysis in beer. And you can purchase these from Labor Veritas or from ASBC, and we have announced the introduction and the release of these standards in press releases, for example, in the Brewing Science Journal. And here, now you have the chromatogram that you get from a dry hop beers with this method. It's much more complex, as you can see here. The pink numbers are the well-known isohumulones we also have in the non-dry hop beers, but in addition, we now have the humulinones, peak 7, 8, 9, before and in between of the isohumulones, and we have the green marked numbers 10, 11, 12 for the humulones, and there is another peak number 13, and this is xanthohumol. It's a very small peak in this case. The concentration is rather low, and the detection wavelength is not optimal. In the optimum for xanthohumol, it's 217 nanometers for this method. It's suitable for iso-alpha acids, humulinones, and humulones, but not for xanthohumol. And if you now have a look on this fraction of the chromatogram of this part between 20 and 26 minutes, and you see here this part not at 270 nanometer detection wavelengths, but at 370 nanometer. So the same beer, only a different detection wavelengths. And here is the co-elution. We did a co-injection of this dry hop pale ale with the new international calibration standard for xanthohumol. And you see this peak is clearly this xanthohumol peak, and you can clearly identify this xanthohumol using this wavelengths. And it becomes very obvious that 370 nanometer is the best wavelengths. If you have a look at the UV spectrum of xanthohumol, we have a minimum at 270 nanometer, but a maximum at 370 nanometer. And as I told you, the concentration of xanthohumol in this pale ale is rather low, but we know that roasted malt can have an influence on the xanthohumol content and on the content of other bitter resins. And just as a comparison, here the concentration of xanthohumol in a dry hopped stout beer, and it's 8.6 milligram per liter. And in this concentration, you have a clear contribution then to the taste that can be expected in this concentration. There is also some influence on the concentration of alpha acids. So fractions of roasted malt seem to act as a carrier, especially for more non-polar compounds. And you can find higher concentrations of non-polar compounds, especially xanthohumol, in dark beers and especially after dry hopping. So this can be relevant for this beer. As a summary, the method 947 is suitable not only for the hexa, tetra, and rho isoalpha acids and for the isoalpha acids, but also for humulinones and alpha acids. For all these compounds, you can use the method as it is, detection wavelength 270 nanometer. But if you are interested in analyzing xanthohumol, you have to detect at 370 nanometer. So the first question is answered now. Hop resins can be analyzed with an existing EBC method, and this is very good news. So it's very straightforward to analyze dry hop beers on the resins. The next fraction are the hop flavonoids, and the question that I would like to raise is HPLC-UV possible, or do we need HPLC-MS equipment? We already have an answer in-house for this question. In 2017, we have published the result of our investigations. The result was that we need LC-MS analysis and detection of hop flavonoids in these dry hop beers. And I would like to give you some more information on this compounds now. And the compounds that we were interested in are the ones that come only from hops. So we did not consider the compounds coming from malt, but only the ones coming exclusively from hops. Xanthohumol can be considered as a resin compound, but at the same time, it's also a flavonoid, and especially it's a prenylated flavonoid. And this is the prenyl group. This is marked here. And this makes this compound special. It is both a resin and a flavonoid. Another compound is the co-multifidol glucoside. And this is an intermediate of the biosynthesis of alpha and beta acids. And I marked here this side chain. And the main compound you can find in hops is the co-homologue. But there are also N and AD homologues of these multifidols present in hops because they are intermediates of the biosynthesis. And then we have the camphorol glucoside and the quercetin glucoside. The two compounds are very similar. Only the R1 and the R2 or only the differences in the R1 side chain. In one case, it's the hydrogen, and in the other one is the alcohol group that you have here. And these compounds are widespread in the plant kingdom, but not present in barley malt, but in hops. And therefore, if you have these compounds in beer, they only can come from hops. And the R2 side chain is the glucose, like for the co-multifidol glucose, and this makes the compounds better water soluble and so on. What is the influence of dry hopping on the concentration of these compounds? Here again, our pale ale, only kettle hopped with the Hallertau tradition, pellet type 90. And this is then the concentration after dry hopping with the US Bravo. You see an increase in all compounds. And if we compare this concentrations with the taste threshold published by Dresel in 2015, you see that especially after dry hopping, you get higher concentrations as compared to the taste threshold for the glucosides. So per definition, they are clearly key bitter compounds now. Only for xanthohumol, you are lower than the taste threshold. remember in the stout we had a concentration of 8.6 milligram per liter, and therefore for the stout it would be a key bitter compound. So therefore it makes sense to analyze these compounds in dry hop beers as well. And these are some characteristics of our published method. It's an HPLC gradient method. The column we use is given here. The detection is in the negative ion mode. We use the following internal calibration standards: dicamba, bentazone, and nicarbazine. And we do a very straightforward sample preparation. We dilute the beer sample with the HPLC solvent and do this analysis. All these details are described in our published method. So the next answer we have is that for hop flavonoids, I would recommend this HPLC-MS method or another one, a similar one, but we know this method that we have published that works. Now we come to the hop aroma compounds. The question that I raised before, can we do the analysis by flame ionization detection, or is it necessary to do the GC-MS? Is headspace suitable, or do we need another sample preparation, or do we even need GC-MS? In 2018, a review article was published by Niels Redberg and Leif Alexander Gabe, and I am one of the co-authors. And we have presented many different methods for hop aroma compounds analysis in hops and in beer. And in the end of the abstract, you see that this review summarizes approaches commonly used for analysis of hop aroma compounds in hops and beer. And there are many methods. For those who are interested in some background information on the pro and contras of different methods, I can recommend this article. In our house, we have already decided before this review paper that we go for a headspace trap GC-MS analysis of hop aroma compounds in beer. We have published this method in the Brewing Science Journal in 2016. GC flame ionization detection is not possible. You can isolate an essential oil from hops and dissolve it and do this analysis, but the low concentrations you have in beer, it does not enable any GC-FID detection method. It's not selective, it's not specific, and so on. So you need definitely MS detection for beer analysis. And we have combined our GC-MS with this headspace trap autosampler. So in the autosampler, there is a trap collecting the volatile compounds. In the meantime, the EBC has already organized a collaborative trial using this method. Also, some labs from America, from the US, participated in this collaborative trial. And this method is since 2 years already recommended as method 9.49, hop aroma components in beer by headspace trap gas chromatography. But it's only a guideline method because in the end, we did not get enough results. So only a few participants reported their results and no statistical evaluation was possible. So we have no data from an international collaborative trial. But as a starting point, I would recommend to use this method for those that just start and think over how to analyze volatiles in beer. Some details on the method. As you know, headspace is the most simple sample preparation for a beer sample. You take 5 milliliter from your sample, you add some salt to get a saturated solution in the end, and you add some internal standards. In our case, for our method, we have labeled standards, and then you heat up this vial, in our case, to 85 degrees, and then you get a separation between a liquid phase and some molecules in the headspace. You have to wait until you have this equilibrium, and components with higher molecular weights are less volatile, so they are enriched in the liquid phase, and the volatiles are enriched in the gas phase. And then this is the sample is then injected to the GC, and before that we have the trap collecting all the headspace before GC injection. Which compounds do we analyze by this method? We have published the method already in 2016, and we started using the method maybe 5 years before. And we covered quite a range of different compounds. Here are some examples. And we analyzed many, many different beers. And in the end, we found out that some of the compounds mentioned in literature are not detectable. They were not detectable at all in any of the beer samples we analyzed. And there is another group in the column in the middle. We only saw minor differences between different dry hop beers with regard to these compounds. And a smaller group given in the first column showed real significant differences. And therefore, we mainly focus when we analyze dry hop beers on these compounds of the first column with the significant differences given in different beer samples. And I have marked red the compounds that are known from literature as key aroma compounds. These are the papers I mentioned in the beginning from Japan or from Fridge that verified them as key aroma compounds. So linalool, geraniol, myrcene, and the ester 2-methyl-butyl isobutanoate are the most important compounds for us. And let's have a closer look on them. Now we again have our pale ale only kettle hopped. These key hop aroma compounds in beer, myrcene, linalool, geraniol, and the ester are only present in very low concentrations. Only linalool is above its aroma threshold, which is about 10 ppb. Myrcene is lower than its aroma threshold. Also, the methyl-butyl isobutanoate, it's below the limit of quantification, and geraniol is not detected at all. And after dry hopping, with 300 gram per hectoliter, we get a clear increase, and this dry hopping was done with the US Bravo again. So you see the clear increase with dry hopping, and if we add even more of the Bravo, as is shown in the next slide, 500 gram per hectoliter, there is even more increase. And the message is that the increase of these key aroma compounds is dependent on the amount of hops and the type of hops, of course, used for dry hopping. But the more hops are added by dry hopping, the more compounds of these key aroma components are present. Bravo is a hop variety containing geraniol, and therefore you see this increase in geraniol as well. Now we go to the fraction of the thiols because they are very special. They are present in beer in very low concentration, and they have aroma threshold in very low concentration. And therefore, it's not possible with our method to cover these compounds. There are several papers on the analysis of thiols in beer. I would like to mention one of them. This was presented at the EBC symposium in 2018 by Niels Redberg of VLB in Berlin. Title of his presentation is Rapid and Solventless Analysis of Thiols in Brewing Samples. And he uses a headspace solid phase microextraction with the on-fiber derivatization of thiols using a specific reagent. And this is then combined with GC-MS. So a rather sophisticated equipment. And thiols known from literature as key aroma compounds are, as I mentioned before, the 4-mercapto-4-methylpentanone, the 3-mercaptohexyl acetate is another one known from literature, and the 3-mercaptohexanol is another one. And you see here the chemical structures of these compounds. The sulfanyl group, SH group, is marked red here, and the sulfonyl group is identical to the mercapto group. So this is a synonymous, and therefore in some papers or some people, they describe these compounds as, for example, 4 or 3 SHA 4SH, because they refer to the sulfonyl group, but have in mind this is always the same compound. And I am mentioning this method of Niels Redberg here because we had sent him some samples for analysis recently, and in my webinar talk 3 weeks ago, I reported on composition of New England IPAs, and in the lab of Niels Redberg, he did the analysis of these New England IPAs. We analyzed 6 of them, commercially available New England IPAs from the US that were covered in the study, and he analyzed them on these 3 compounds, the 4-MMP, the 3-MH, and the 3-MHA. And you see here, the concentrations are in ppt nanogram per liter. Therefore, our headspace trap GC-MS method is not sensitive enough. Therefore, you need a more sophisticated equipment like the method of Niels Redberg. And just to give you an impression, you see here the differences, and quite high differences in different commercial New England IPAs. The highest concentration for the 4-MMP is 149 nanogram per liter, and the aroma threshold is only 0.5 to 1.5 nanogram per liter. So it seems to be a very clear contributor to the aroma impression. With regard to the 3-MH, the highest concentration detected in these beers was 37 nanogram per liter, whereas the aroma threshold is higher. And with regard to 3-MHA, it was not detectable in any of the beers. So conclusion for me is that 4-MMP seems to be the most important thiol in dry hop beers. So we are now a step further. We know with regard to hop aroma compounds, for the PPP range, the equipment can be quite simple. Headspace trap, for example, combined with GC-MS. There is already an existing EBC method, a guideline method. But for thiols in the PPT range, you need another sample preparation. Direct headspace is not possible, also not in combination with trap or SPIMI. You need some further on-fiber derivatization, and you definitely need the combination with the MS-MS. Yeah, this is then already more or less the summary and the end of my presentation. Again, one slide that summarizes what I told you just before. For hop resins in the ppm range, the HPLC-UV is the method of choice, according to my opinion. For the hop flavonoids in the ppm range, we have the HPLC-MS method. For the hop aroma compounds in the PPP range, like the terpenes, the terpenols, esters, and ketones, headspace trap GC-MS is the method of choice. But for thiols in PPT range, you need a more sophisticated method. For example, the method of Niels Redberg, the headspace SPIMI on fiber derivatization. Okay, so this is the end of my presentation. I would like to thank you for your attention, and I would like to say thank you to the whole Hopsteiner lab team that did all the engaged development work on working on these methods. And I would like to say thank you to all participants in the various ring tests we always organize in EBC, and without such participants, it is not possible to do method development and method recommendation by analysis groups. So this is the end of my presentation, and I would like to give the word now to my colleague Sandro for the Q&A session. Okay?
Yes. Thank you, Martin. I'm also back again. Thank you. Very interesting. This gives a full overview which kind breweries should think about equipment and possibilities to cover the analysis regarding aroma or bitter substances. So thank you very much for this. And we have some questions came in. Maybe I just start with one that you just mentioned when you showed the slide about the New England IPAs and the studies about those. You mentioned especially the 4-MMP is one of the most important thiol coming from the hops and also relevant in those kind of beers finally. Do you have some more information about the sensory characteristics of those components, especially the 4-MMP?
Yeah, of course, we have some informations. This component, for example, is known for its fruity character, and the New England IPAs are connected with some, or are known as fruity beers, and therefore 4-MMP seems to play an important role for it.
Mm-hmm.
Yeah, in this talk on the New England IPAs, I gave some more informations on the typical sensory of the various fractions. I didn't want to cover this in this talk again, and would like my goal was to really focus on analyses. But all these compounds that I mentioned, the 4-MMP and the linalool and the geraniol, they are not only because they are key aroma compounds or key bitter compounds because of their concentration. Their aroma or bitter profile is well known and is known to contribute to the overall taste or aroma impression in beer.
Yeah.
And these are all, yeah. So in various beer styles, you can find different concentrations of them.
Yeah. Okay. And just another question about those components. Are there any specific varieties that contain high amounts of those components? Is there a special group or something?
Yeah. Okay, as you can see from our studies, we judge really the 4-MMP as the most important one. Let's say the lead compound for the fraction of thiols. We are fully aware that there are many others. There are also precursors and so on. But 4-MMP is, according to my opinion, can be kind of lead substance. And because it has this very low aroma threshold and you can find high concentrations in beer. And therefore we were interested in analyzing a range of different hop varieties on this compound. And the study was done by the group of Professor Steinhaus and Dr. Klaus Reglitz at the Technical University in Munich. And such a paper is published. You can find in Journal of Agriculture and Food Chemistry, and there you can find huge differences in different varieties with regard to 4-MMP. They use also a very sophisticated method. They have also developed a method for beer analysis. They use GC-MS, another technique suitable for analyzing thiols in beer. But there is information available. And if somebody is interested, I would like to share this information then.
Mm-hmm. Very good. Okay, thank you. A question that came up 2 times is what about the IBU method? You didn't mention something about this in case of dry hop beers, so maybe you'd like to comment on that.
Yeah, I didn't mention it because I expected the question in the end. Because that's a very interesting story, and you could give another talk about this. In the end, remember the compounds introduced by dry hopping in addition to iso-alpha acids. These are mainly the alpha acids and the humulinones, and they are detected at 270 nanometers. And this is quite similar to the measurement of BU wavelengths. And so you have a clear contribution of these compounds to the BU value. And therefore the BU value, the IBU value in a dry hop beer does not correlate with the iso-alpha acids concentrations only, but the IBU value also reflects iso-alpha acids plus alpha acids plus humulinones. And therefore, the IBU value can be misleading if you want to make any conclusion about the expected bitterness, because humulinones has a bitterness of about 66%, or this is the literature data, 66% as compared to iso-alpha acids. Alpha acids are quite lower, about 10% as compared to iso-alpha acids, but they contribute to bitterness and to the IBU value. Therefore, you are confused. My recommendation would be you can use the IBU just for quality control to make sure that you have added always the same amount of hops. And if you don't change the recipe, of course, you can control the quality of the beer by IBU. But any conclusion and any discussion about bitterness reception, bitterness intensity can be misleading.
So maybe, thank you for the explanation, and maybe this is also the answer why you can drink from time to time. You find in the supermarket 100 BU beers, and maybe that's the reason why you can still drink them, because it's not 100 ppm of iso-alpha.
If it would be 100 iso-alpha acids, yeah,
I guess it would be a little bit harsh. Okay, picking up the issue that there are a lot of alpha acids solved in the dry hop beers. The question came up: is there any connection to the foam of dry hop beers? Do you have some more data on that? What do you think? I mean, it's a controversially discussed issue.
Yeah, of course. Yeah, in the end, of course, alpha acids are improving the foam, but after dry hopping, you get such a complex mixture in the end. So we have maybe foam stabilizing effects like alpha acids and destabilizing effects. But alpha acids in principle would be positive for the foam, but this is not the only factor introduced by dry hopping, and therefore it's not possible to say the foam is improved in dry hop beers because alpha acids are present. It's a contributor to better foam, but there can be another fraction that is not going in this direction. What is your conclusion, Sandro? Foam improvement by dry hopping?
Well, in most of the studies we see there might be a little influence on the one or the other side, but the dry hop beers in general, they have such an, from the malt and already and everything, they have such a high amount of higher molecular proteins that they already contribute very good to a foam. So I hardly find dry hop beers that don't have a good foam. And comparing the amount of hops added by dry hopping, I would say there are slight changes either in the one or the other direction, but in principle the foam is still pretty good of those beers. That's my experience.
So usually you have no problems with foam, and therefore the question is whether you need the alpha acids. Yeah. Okay.
Okay. Then also picking up the UV spectrum method again with regard to polyphenols. There's the EBC 911 for polyphenols in beer, and the question came up: is this also suitable for the total amount of polyphenols in dry hop beers, and how much is the impact of the polyphenols on those kind of beers?
Okay, by this method, of course, you mainly measure the catechin type flavonoids and polyphenols, which are mainly introduced by malt. About 80% of this type of compounds coming from malt, and only about maybe 20% from hops. Maybe the ratio is higher with regard to dry hopping. But this is a very unspecific method. Like the IBU method, it's unspecific. This method is unspecific, and it doesn't really help. And we analyzed many dry hop beers on polyphenols, and we did not see any clear correlation between this parameter 911 polyphenols and dry hopping rate. So I think this is not a suitable method for dry hop beers.
Hmm.
Maybe also with regard to quality control, that you can judge the consistency of your brewing process. Yes, but not
Yeah.
for product development or something like that.
Yeah. I mean, there's a lot of ongoing things. If you dry hop a beer, also on the polyphenol side, in the cold section of beer production, you have a lot of more troop formation.
Yeah.
Then also in the bottle afterwards, there's some sedimentation can be found and so on. So probably it's rather difficult to deal with the polyphenols. And yeah, I even know breweries they filter the dry hop beers in the end just to make, yeah, or the market demand is that the beers should be filtered, and then it's not a big deal anymore. Yeah. Uh, in the end, you mentioned the slides about the increase of myrcene, linalool, geraniol, and 2-methylbutyl isobutanate when using 300 gram per hectoliter, and then you compared it also with 500 gram, and you mentioned the more hops you add, the more of those relevant components you get into the beer. Is there kind of a linear behavior, or what do you think? Is it difficult to say for each component because there are different solubilities, or what is your experience?
Not that there is quite a linear increase in dependence of depending on the dry hopping rate. Of course, if you get concentrations for linalool higher than maybe 1,000 or 1,500 microgram per liter, but this is not in the end not possible, because then you have to add maybe several kilograms per hectoliter. But in the usual range for dry hopping, you have a linear increase according to our experience for all the hop compounds, for the polar ones, but also for the non-polar ones, and also for the thiols. This is our experience. Yeah.
Okay.
It's quite linear. Yeah. It's quite linear.
Okay. Another very concrete question regarding headspace analysis. So is there a problem that components might decompose when headspace analysis is performed at a high temperature, such as 85 degrees?
Yeah, of course, we carefully looked at this, but we did not see any degradation. So we are adding the labeled standards. So usually we have for myrcene, for linalool, for geraniol, and also for the ester, for the main compounds that we focus on, we have the deuterium labeled forms, and therefore, so we do it before heating up. So we have the similar behavior of the analyte, of the parameter to be analyzed, and the internal standard. And this maybe also helps to control the whole analysis, but we do not see influence of the temperature. No losses at this temperature.
Okay. Another question came up about xanthosumol, which is increasing after dry hopping as well. You mentioned there's only the chance to get very high amounts with a roasted malt. So in case of a, let's say, dry hop beer used, where roasted malt was used, do you think the range gets into a range where you can claim something about health, considering this would be an alcohol-free beer, or what is the latest research on that?
The positive news is that currently we have clinical trials going on with xanthosumol, and in the end, if you have results from clinical trials, you can really, this is then a reasonable basis for any health claim. And I don't know at the moment the active concentration in human beings. I don't want to speculate at the moment, but we will get some data very, very soon. And then we will see whether a concentration of a few milligram per liter, maybe then a few milligram per day, is enough for any health effect. In case this would be the right concentration. Nevertheless, of course, as you mentioned, it's not not very good to give a health claim on an alcoholic drink. I would say it's impossible. To give it in an alcohol-free beer would be possible, but in the end, I think the brewing industry could benefit from the positive effects of xanthomol more indirectly. So if there are some products, functional foods, or maybe medicines with xanthomol, and you can say you have the same compound in beer, this could be enough for improving the health image of beer.
Okay.
And
well,
maybe
yeah.
Do we still have time? Yeah, maybe.
Yes,
Because
yes.
one comment, it's not only the stout, by the way, which has high concentrations of xanthomol, but also the New England IPAs. And this is because in New England IPAs, you have the haze as a carrier. It's not filtered, so the haze is not removed. It's there, and you have a lot of haze because of the oat and wheat proteins, and we could also find very high concentrations of xanthomol in New England IPAs, which is actually absorbed to the haze. But if you drink the beverage, you get the xanthomol as well.
Okay.
Okay.
Well, I guess the xanthomol topic itself is a whole webinar to be held separately.
After we have the results of clinical trials.
Okay, so we wait until this day.
Sandro.
Okay, then
maybe
we have
we wait a few months.
Yeah. Okay. We have a final question, which is directly to you and your people in the lab. So, is there the chance to send samples to verify our internal results when we are developing such new methods? So, what do you think?
Yeah, in principle, we are very open. It's a question of how many samples we get and from how many people that send in samples. Maybe some people of our lab are listening to this webinar, and I have to be careful to give the right answer because they have to do the work in the end. But of course, we are open, and you can approach us. And I am interested that these methods are introduced in the brewing industry because we believe in them, and therefore we are open to help. Please approach us.
And on the other hand, there's also the part, I guess, to join the collaborative trials which are organized.
Yeah, very good hint, because the working group of Hop Analysis is organizing collaborative trials, and we have also a collaborative trial on dry hop beers, aroma compounds in dry hop beers, for example. And everybody can join this collaborative trial. Please send me a message, and I can organize this.
Okay.
Yeah.
Perfect.
Good hint. Very good hint. Yeah.
Okay, so these were the questions from today. I would say we close the session for today. If you agree, Martin, or anything from your side?
No.
Okay.
The hops are grown 1 centimeter, I think, during my talk.
Good to know. Okay, so then that's a good hint for the next week. So what do you guess in 1 week? How much more centimeters will they grow?
I don't know. I have to calculate. Okay. 2 hours times 6.
Okay, very good. Okay, next week we will talk, our technical director, Frank Pfeiffer, will talk about hops beyond the conventional usage as we know it from beer production. So it will be very interesting as well. We hope you enjoyed the time with us today, and you will join us next week at the same time. As you usually get an email afterwards, you know, there's a link to see the record of the video from today. And yeah, we are looking forward to meeting you next week. Take care, all the best, and stay healthy. Bye-bye.
Bye-bye.